So this is me, S.Farrell, and the link colors are weird, but there you go. So I'm from Trinity College Dublin. I'm mostly talking today about the kind of process stuff, about what happened as we were implementing this, rather than so much about what Encrypted Client Hello is, but there's a bit of that. And let's do it. So the point of view here is essentially what we did was we were implementing this spec that's been developed in the IETF over years and years and years and years, sadly. And we were basically trying to implement it and then offer code to various projects to get that functionality into their code bases. So we're kind of outsiders trying to work with maintainers, and that's the point of view of this presentation. There's probably some lessons to learn for the IETF as well, but that's a different talk. I won't complain about them as much as Peter did yesterday. And so there's some obvious and generic lessons. One thing is, if people want to kind of comment or ask questions as I'm talking, I think that's fine. The audio-visual people will probably panic. But if you have any questions or comments as I go, just please put your hand up or just say them, and I can repeat them back to the crowd, rather than wait to the end. So feel free to go ahead. Anyway, the first lesson, I guess, is don't try and do huge changes, which is kind of obvious, but unfortunately impossible in this case. It turns out that Encrypted Client Hello touches listed in the OpenSSL code base. It touches lots and lots of files. It needs lots and lots of lines of code. It changes lots and lots of things deep in the internals of the TLS engine. And so, sadly, we couldn't actually do the sensible thing and make small changes. We could, however, do that for things like Apache, Nginx, and so on. When you get to the kind of application layer outside of the library, the changes are actually reasonably small and much easier to process. So that's kind of much more pleasant and following the right approach. Another lesson we kind of learned was that all of the different upstream projects, OpenSSL, etc., they all have kind of pointlessly different styles. Somebody wants something tabbed here, over there, and when you go to the next project, they want it done differently. Somebody has a style of providing certain types of APIs, and they like to kind of keep with what they're doing. And so you end up kind of having to live with these kind of, from the external point of view, irritating kind of pointless things that have to get to various people's CI kind of jobs and so on. But in most cases, the maintainers are very helpful. That if you start out and you provide a bit of code, and one of the first things they'll say is, this doesn't adhere to our code style. And then sometimes they'll say it very nicely, and they'll say, here's a tool that you can use to kind of do a lint kind of thing. Other times they won't be that helpful, but generally they're pretty helpful. And so if you're trying to contribute to lots of different projects from a single kind of source, then you'll end up making these pointlessly different changes, but it's not too bad. And a less obvious lesson maybe is to be nice. Being nice seems like an easy and obvious thing. But continuing to be nice as you're kind of interacting over multiple GitHub PRs or issues or mailing lists, it sometimes requires a little bit of control or self-control, and that's very, very useful. And in fact, it's also kind of quite reasonable, because we're kind of offering a piece of code to these people. They're going to have to live with it for an awful lot longer than we will. So you kind of give them a bit of deference, and things kind of go a lot better. Although it can get kind of tiring when things take a long, long, long time to get processed. But sometimes just take a big deep breath and then kind of be nice is well worth it, because if you're going to get frustrated, then that's not going to help, and you'll just be frustrated for a very long time. So just take a deep breath and go ahead. It's better. It's also sometimes a little bit difficult to know if you're kind of contributing to some project and you're starting. It's kind of hard to know who's who. So, for example, you don't know who is the person in, it took me a while to figure out who in the OpenSSL project actually knows about which bits of the code. And so it's a little bit hard sometimes to figure out who's in control and to whose comments should you pay most attention. Sometimes you get kind of random comments, and they can be good, but not always. Sometimes they might actually send you off in the wrong direction. So figuring that out is kind of useful, not too hard. But then also you kind of have to bear in mind that a lot of times there's other people just like you who are not maintainers but are kind of interested in the code base and are just randomly commenting, and you may as well be nice to them as well. So what's ECH? How many people kind of already know what ECH is roughly? Okay, it's a good few, but not everybody. So in the TLS ClientHello, we have the server name indication, which tells the server which private key to use for the TLS session. And the SNI is essentially a privacy leak. And we knew it was a privacy leak all the time. And we've always wanted to kind of fix it. And until relatively recently with TLS 1.3, and with the advent of DNS privacy mechanisms, it kind of wasn't really sensibly fixable. But now it is. And so the basic idea is to be able to patch this kind of small remaining privacy leak in the TLS ClientHello message by encrypting the SNI. And the internet draft is still an internet draft, not yet an RFC, sadly. Started in 2018, believe it or not. You can see all the various versions that have existed up to version 25. And essentially, it's the specification for how to do this encryption. Now, the hard part about this encryption is you want to encrypt something in the first message. So it's kind of, you need something to do before you've spoken to the server. So the basic mechanism is that the client doing TLS 1.3 somehow, probably from the DNS, gets a public key to use to do this encryption. And that public key is called an ECH config. And it's typically going to be published in a HTTPS resource record for a web server if you're dealing with a web server. But ECH should work for other protocols as well, although it's kind of less clear where the benefits are in some cases. But nonetheless, the way it basically works is the client will do a DNS query, get a public key, encrypt the parts of the ClientHello, and then the TLS protocol kind of should go more or less the same otherwise, and more or less does. So I got involved in this. I thought it was kind of a straightforward, simple enough thing. And it started out simpler than it ended up. So as I said, for a long time in the IETF, people working on TLS 1.3 wanted to be able to kind of close this privacy gap and be able to encrypt the SNI. And there's an RFC that documents the kind of some of the ideas about it, some of the reasons why you want to do it. For example, SNI can be used, it's used in certain countries for censorship. It can leak information that basically you don't necessarily want to leak. So there's a censorship angle here. There's also just a general wanting to kind of close the security gap. And the initial drafts didn't actually talk about encrypting the ClientHello. They just wanted to encrypt the SNI as a new TLS ClientHello extension. And that was relatively simple. And around that time, I was kind of retiring from being a standards bureaucrat. I don't know if Peter Gutman's in the room or not, but I was looking for something to do, and it turned out nobody was coding up ESNI for OpenSSL, so I started working on that 7 years ago, which is kind of pretty sad. And implementing ESNI wasn't very hard, because it was essentially just a simple, straightforward enough extension, and you just had to replace the outer, the server name indication with something else, and add a new extension, and then do the decryption on the server side, and it was lovely. So that would have been relatively simple, and we might have actually been able to get things deployed much more quickly had we just stuck with that, but we didn't. Nonetheless, as part of doing this, it's always kind of useful to have a few quid, and it's also even more useful to have kind of deadlines and deliverables, those kind of things. So we, as soon as we kind of figured we'd like to kind of implement this, and then offer code to OpenSSL and maybe to other people, we said, OK, let's make a little project. And we started this DEFO project, funded by the Open Tech Fund, who are really, I advertised for them. They're a really good funder. And they're especially good at no-cost extensions. And I think we've done that 4 times now, because the IETF process and the OpenSSL process has all been so slow that we keep having to add these no-cost extensions to the contract in order to keep going ahead. So basically, the project's goal was to implement ECH, encourage other people to implement it, do kind of little trials, do interoperability testing, and so on. And a non-goal was we didn't want to create a new project that lives forever. So that's an absolute non-goal, which kind of makes it interesting, because we don't want to live forever. We actually want to get rid of the code and kind of move on to doing other things, and then let people who kind of take over this code kind of live with it and prosper. So the lesson there, I guess, is if you're going to do something like this where you want to add a feature to various things, it's quite useful to have some class of a project or a contract. And it's not very much money. It's not for millions or billions. It's like tens of thousands. But it's still very useful to have that kind of structure. And funders like OTF, or I think the Sovereign Tech Fund, the kind of next generation internet thing. These kind of funding models where you get like a little bit of money with very few overheads, that really work well for this kind of project. It's also kind of handy to have people to work with, because that keeps you kind of going, especially if you're doing something that's actually going to take years. If you're just doing it by yourself, it would be very easy to get kind of fed up and just move on to something else. Whereas if there's a team of you kind of working and chipping away at this, it makes it easier to kind of continue for the years that it actually takes. And we actually got quite lucky. We were working with people from the Guardian project is kind of a loose collective of people working on internet freedom technologies. And we kind of got lucky in that some of them were very good, and they had, various people had lots of more skill in setting up CI systems and so on. So in the DEFRA project, we have a kind of a CI setup that daily kind of merges our code with the upstream for various projects, runs tests, and that allows us to detect things kind of pretty nicely. So for example, one of the issues with working with OpenSSL is that OpenSSL keeps committing things, because there's lots of people doing stuff. And so you end up having to rebase quite a lot. And doing that manually is really a pain. And if you don't do it often enough, by the time you come to do it, there's some kind of merge problem. And mostly those are kind of pretty straightforward, but sometimes they're very subtle. And so with the kind of CI setup we get an email that says when there's a merge problem every day when they happen. They happen maybe 2 or 3 times a month. And that kind of is very helpful in kind of knowing when there's going to be an issue with integrating the code because of upstream changes. So having a little project is good. And what's the kind of scope? Essentially, we're working to ECH-enable things. And so we've kind of upstreamed code into curl, Lighty, Apache. You probably know what all those are. Uni is a internet kind of measurement censorship, anti-censorship kind of project. And so one of the things we kind of help them with is they have their Uni probe, which is a tool you can install, which will then, from whatever network you happen to be in, will access various URLs from a curated list to see which of them are blocked in that network. And then they have a kind of a dashboard that kind of reports on who's blocked where. And so we've helped them with adding a ECH probe so they can check, is ECH blocked or not in certain networks. Conscript is a kind of little library thing on Android. And then also Free Nginx is kind of interesting. That's the first case where the maintainers, I guess, looked at some of the work we'd done with Lighty and Apache and so on. And then they wrote their own patch to add ECH to that Nginx fork. And then we have ongoing work with HA Proxy, Nginx, and CPython to kind of ECH enable those. And in a lot of cases, like I said, adding ECH to the OpenSSL library is hard and complicated and a pain in the ass. Adding it to these applications is relatively straightforward for the web servers. Typically, it's only about 400 lines of code. You add a new configuration setting to say where the private key is, and you integrate that somewhere, and there's like an extra API call to say load the private keys for ECH. So it's pretty straightforward for web servers. In the case of clients, it can be much more of a problem. So with curl, for example, curl has had a very simple model of how it uses the DNS. It's essentially just doing get header info and caching that. Whereas now, if you're doing ECH, the client has to go and fetch this HTTPS resource record and cache it. And you're doing that kind of at the same time as getting A and quad A's. And if you're doing it in terms of like libcurl, you might want to do something entirely different than curl currently does. So the DNS parts of clients can be quite tricky. In curl in particular, where the client has a very basic model of how to use the DNS, it's a lot of work to get that right. In particular, because the DNS records that are used for this, the HTTPS resource record, essentially has a new kind of pointer, a CNAME-like thing that could actually, it's called an alias mode record, which you might involve chasing those across the DNS, which is kind of really tricky to do right for everything. And I'm not sure if many people have done it right for everything. Even browsers haven't done it particularly well so far. In the case of CPython, it was actually pretty straightforward because CPython has another Python library for dealing with the DNS. So again, that was pretty straightforward. So again, there's lots of the complexity is in the library here, which is good. The other kind of takeaway from working with those was that there's multiple TLS libraries in the world that are important. In particular, let's say with curl, curl supports OpenSSL or Boring SSL or Wolf SSL, which is their own kind of SSL library aimed at embedded systems. and a few others. Similarly, on the web servers, more and more of them seem to be adding support for AWS LC as an alternative, which is kind of like a wrapper around boring SSL with version numbers, which I guess makes it more interesting. So in some cases, we've basically helped them work with boring or with other SSL libraries. In other cases, they've done it themselves. And there are differences in the API calls that are added for ECH. So the boring has a kind of relatively straightforward and simple model. The model that we've ended up with for OpenSSL is a little bit more complicated on the server side, but is kind of API kind of compatible on the client side. We've also done kind of interop testing and helped the developers as they were adding ECH to Golang and Rust TLS. And we run interop testing with those guys. So I guess the lesson there is, even though OpenSSL is, like for our little project, it's the main target, there's still other TLS libraries in the world that are important, and don't ignore that. So I said it started out simple, more or less did. We had this encrypted SNI extension that there was a kind of a transitional phase where it was called Echo, and then it was called ECH. And essentially what happened was that the early ESNI drafts used a kind of an ad hoc way of doing the encryption. And they also used the DNS text resource record for the public key. And both of those things were kind of considered bad. And what tended to happen was, if you're adding the encrypted client Hello or the encrypted SNI as a new extension of its own, you have to kind of worry about that being stripped out and patched into somebody else's client Hello, and you don't want that to work. And you also will run into issues if you hit a hello retry request in the TLS protocol, where the initial client Hello, it has key shares for a group that the server doesn't like, but both client and server support something, so you start over. And both of those things kind of create complexity in terms of taking the simple approach turns out to be not necessarily working always, or might have some kind of security issues, because you just don't want that encrypted blob with the SNI to be extractable and injectable into some other client Hello and have things work. So one of the things that was done there was the method of encryption. Like I say, it was very ad hoc initially. And people don't like doing ad hoc encrypting things, so we went and a bunch of people developed this thing called HPKE, which is RFC 9180, which essentially is a way of doing what you want to do. I have something I want to encrypt to a public key. So I have a message to encrypt, I have a public key. I want to do that in a reusable way with some nice security proofs, and HPKE kind of does that. HPKE is used essentially then it's how we do the encryption. It's also used by a protocol called MLS, which essentially is doing the kind of messaging that you'd use like with Signal or WhatsApp, that kind of group messaging. So it has other uses as well as ECH. And as usual, unfortunately, RFC 9180 has way too many options. There's different modes. There's an authenticated mode. There's a base mode. There's all sorts of things. There's 96 different options, basically, in that, if you include the different algorithms. And that was a pain in the ass. But we implemented it. And so, it turns out, I don't know what the right answer here is. We implemented this and upstreamed that to OpenSSL and did the right thing and tried to implement all the things in the RFC. And that's not the case with others, like NSS and Boring have only implemented the bits they wanted. And the end result is great if somebody wants to use a weird combination of algorithms. The OpenSSL library could support it for HPKE. But sadly, that means that you can easily create non-interoperability. If you set up a server and make a choice of algorithm combinations that are not supported in clients, then you won't interoperate with them. So I'm not sure what the right answer there is, because unfortunately, there's in RFC 9180, there's no kind of mandatory to implement set of algorithms, because people don't like doing that anymore. It's no longer fashionable somehow. So that was a bit of an issue. And it turns out that, even though we lost the argument lots of times, we keep arguing to say, don't add these options, don't add these options, and they keep adding the options. Even though you lose that argument, eventually they come around now to revise HPKE, mostly in order to add some kind of hybrid chem support into it for post-quantum. And they're also going to throw away some of the options, some of the unused things, like the authenticated modes. They'll still be in the initial RFC. They'll still be in the OpenSSL library. I don't know what the right answer is there. Should you keep it? Should you throw it away? It's going to be code there's not much of a code path in it. That's not that. It's really algorithm combinations. But there are code paths there that are probably unlikely to be used much going forward. So I don't know what the right thing for the library is to try and get rid of it or to try to stay compliant, in particular when other libraries and other applications haven't necessarily used all these combinations. So that's kind of probably an interesting maintenance question for the library. Oh yeah, so this was the process of actually trying to give the HPKE code to the OpenSSL folks. And we basically, this is before they went, OpenSSL started with this twice yearly cadence of releases. And so we opened a PR with our HPKE implementation in November 2021. It took about a year. There's about 4,500 lines of code, and I think there was like 1,000 comments on the PR or something. It was kind of an arduous. Now, partly that was my fault, because this was the first time I had tried to add something as complicated to OpenSSL. And my kind of native approach for APIs is to have kind of simple APIs with lots of parameters and simple parameters. OpenSSL prefers to have a more complex sort of structures and various kind of style things that are different. So that took a bit of time, but it also just took a long time because there's a good bit of code to review. And I suspect it's fair to say that it's probably hard for any library and it's to take big chunks of things like this. And I don't know if anybody knows how to do it well. I certainly don't. But I kind of learned a lot with it. One of the things that OTF does that's nice as well is they will actually fund a kind of pen tester to do a code review. And in the case of HPKE, this wasn't that actually hard because there's not a huge attack surface. And they did a review, wrote a report, and luckily that landed before OpenSSL had a release that included HPKE. So the lesson I learned there was stick at it, even if it takes a year and 1,000 comments. You can get there in the end. And it's like somebody who kind of says, like a tourist in Dublin says, how do I get to the general post office? And the answer is, I wouldn't start from here. So that's a kind of a good thing. I think it probably would have been a lot better if I had known the kind of style of APIs that OpenSSL like and written code like that, as opposed to writing code in the style I like and then having to change it to the style that the library likes. But nonetheless, we kind of got there. And also, Shane Lontis was really helpful in this. He kind of stepped in and kind of started working on the code as well. And that was really helpful and kind of sped things up because the OpenSSL maintainers preferred some of the functionality to be kind of deeper in the library as opposed to using existing library calls. And it would have been really hard to figure out how to do that without active maintainer help. So we got a good lot of help there, which was great. So the other thing that happened between ESNI and ECH was the DNS thing. So ESNI initially used a text resource record to have the public key, and that actually works. It's done for some other protocols, but it's kind of manky. And you get kind of text resource records are very overused and polluted by various things. So instead of that, over much time, RFC 9480 was developed, and RFC 9480 essentially defines the HTTPS resource record, or a generalization of it, SVCB. And that essentially allows a website owner to publish information about the kind of things they like. So things, the equivalent of HSTS, they could have group, not yet, but they will be able to kind of publish preferences for which groups they support, all sort of stuff that the browser would otherwise have to guess or possibly waste a round trip to get. And so the HTTPS ORR, it includes essentially go faster stripes for browsers. And this actually is kind of semi-interesting in that if it wasn't for this, browsers probably wouldn't be interested in deploying ECH so much. The browsers are more interested in are more happy with implementing and deploying ECH because they also get the go faster stripes of being able to kind of get information about the web server TLS settings from the DNS before they send the ClientHello. On the other hand, it also creates issues. So I'm currently redoing some interoperability testing we've done in the past. And so what we see, for example, is that Chrome in particular is pretty impatient when it comes to reading this resource record. So with Chrome, currently, in the tests I'm doing, it looks like they'll send out requests for A and Quad A and HTTPS resource records, but they'll only wait something like 100, 200 milliseconds for the answer to the HTTPS resource record, and they'll fire ahead and do TLS without ECH, or with just greasing ECH. And that happens even with the same URL. In various test setups, it seems to happen more than it happens in a real human use of a browser. But if you're using a browser or a headless Selenium Chromium setup, for some URLs, ECH only works 25% of the time. For others, it works 100% of the time. And the why is deep inside the internals of Chromium, unfortunately. And it'd be nice if they did something a bit different. There is some work on a thing called Happy Eyeballs version 3, which is hopefully going to fix this, but that may be slightly longer term. Firefox, for example, has some similar issues, but it will wait a lot longer for the HTTPS resource record answer. And the issue basically there is that we're asking the clients to do ECH to do essentially 3 things: look for an A, a Quad A, and a HTTPS resource record. And the answers may arrive at different times. So clients will always have some issues in doing it, and it's never going to be as 100% reliable and bulletproof. So ECH does work, but it also might not work. And so we did a little, a small trial with the Wikipedia folks where they put ECH on a set of URLs they run, not on the main kind of content, but a set of URLs they run for some testing. And it looked like what we saw in, when was it? About June of this year. We saw about a third of browsers weren't able to do ECH because they're too old or because they're Apple. And about a third of browsers, it all worked just fine. And about a third of browsers could do ECH, but it didn't work in the testing we've done so far. So it's kind of an interesting, it does kind of help with privacy, but it's not working 100% of the time at present. It can work 100% of the time. So in the tests we do, for example, with curl, curl does work 100% of the time. The tests we do with a kind of toy client with Golang and Rust TLS, they also work. It's just essentially, I think, because browsers are such complicated beasts that you actually run into other issues, like the Chromium being impatient. So I guess the lesson there is, as you're trying to do these things, in particular when there's multiple parties involved. And so in the case of ECH, we have the client, we have the server, we have whoever controls the DNS, we have whoever operates the DNS, and these are all different parties involved. And so between all of those, what actually can work straightforwardly and perfectly in the real world is probably likely to have some kind of failure cases. And the rate of those, in this case so far, is still relatively high, which is sad. So you don't control the ecosystem, but understanding the incentives of people is kind of useful. And so, for example, we've also done some work in the DEFO project on ways to kind of make it easier for website owners to publish this HTTPS resource record with an ECH config in it. In that we're working on a spec in the IETF for a way the website can basically publish a .well-known URL that has the information it would like to end up in the DNS. And so that whoever's running the DNS as an administrator can suck that out of the web server, check if it works, and then publish the resource record. Because as in a lot of cases, what you'll find is that the operators of the website and the operators of the DNS are different people. And so they also need a bit of help to kind of glue things together. So we basically had ECH working. We had working code, but not reviewed code for, I don't know, about the last 4 years or so. The specification itself hasn't really changed since the draft 13, which I forget when that was, but that's a few years back. And so we had this working code, and we wanted to kind of give it to OpenSSL, and they would like to get it, but it's a humongous chunk of code. And so we kind of created a PR, and the OpenSSL maintainers, Matt and Thomas, who've been really helpful. I presume they had a look at that and went, oh shit, what am I supposed to do with looking at 15,000 lines of code or whatever it was? And I think around the same time that we created the initial PR, I guess the OpenSSL project were thinking about how do we handle these kind of things that take a long time, and how do we get them into releases? And then they started this idea of OpenSSL feature branches. I don't think this was the first one. I think it was DTLS before this, or yeah. So there's a DTLS feature branch, and I guess the idea is to have a branch that's in the OpenSSL repo that just is working on this feature, and then eventually, hopefully, at some point in the not too distant future, that will end up in the master branch and be fed into releases. And so the process there has been interesting. The feature branch was created about April 24. We've had about 7 PRs merged since then, and the process essentially has been, we had a discussion with the OpenSSL maintainers about APIs, and because they didn't like the APIs I had, which is fair enough. And so we had a discussion about that. We tried to document some APIs. We did that. I tried to change the code to use those APIs, did that. Then I started creating PRs with the actual code, and typically the process has been, I'll create a PR that adds the next bit, and wait, and then eventually Matt and Thomas will get some time and have a look at it. And then at that point it gets processed very quickly, but the wait part can be significant. And from my side of the house, that can be again something that you have to take a deep breath and say, okay, they're just busy. And then we process it. Once they get to pay attention, it's actually fairly quick and pretty painless, and we make changes and it gets done. And then normally the day after I had the next one ready, because in the period while I was waiting for them to respond, I'm getting the next one ready. Sorry. And so the next PR would be created in a day or so, and then we wait again. And so that can be interesting. But we've kind of gotten, it's about 10,000 lines of code in that set of PRs so far, which again is gigantic and horrible, and you shouldn't do it, but you have to for this. That code is scattered over lots of, I don't know, about more than 20 files in the TLS library, and it's kind of, fairly intimately screwing around with things. So, for example, with the encrypted client hello, if you were just going to encrypt the entire client hello and then put it in an outer client hello, things get big very quickly. And so there's a kind of a compression scheme defined as part of the ECH specification that allows you to say, okay, for this extension, it's going to be the same in the outside and inside. And therefore, I don't have to include it other than just the extension number in the ciphertext version. And so there's, basically you have to touch every extension handler to say, do I want to actually always duplicate it, never duplicate it, compress it, or whatever. So it's a sad part of I think there was probably a mismatch there where there wasn't sufficient familiarity with the people writing the specification with the implementations. At the point they were writing things, that they didn't really see that this was going to be so invasive. We probably could have done better on the standard side as well. Anyway, so the main lesson here is that the response times of maintainers are bursty. I think is a way to describe it. And it would be nice if there was, if this was better. I don't know how you solve that. I wouldn't even try and suggest it, because I'm sure OpenSSL maintainers are busy in all sorts of ways. But it's a definite thing that I presume, the OpenSSL folks would also agree that processing relatively complicated things like this, or extremely complicated things like this, is tricky, and getting the time to do it is tricky. There's probably not that many people on the OpenSSL maintainer side who are familiar with all the bits of code, because it's changing so many bits of code. So the response times can end up pretty bursty. So, again, though, Matt and Thomas have been really helpful and a pleasure to deal with when they get to spend time on this. So that's good. Okay, so overall, it's a really time-consuming process to do this, and it takes, there's a long duration here. Like, I started this 7 years ago, believe it or not. And it can be a little bit frustrating when you're dealing with lots of different upstream projects. Again, individually, people, when they pay attention, are usually a pleasure to deal with. But I have to say, some projects are easier to deal with than others. And again, sometimes if you're dealing with, let's say, with curl, they have a nice way of adding what they call experimental features. And that actually eases the process as well, because they're happy to take in stuff, have it as an experimental feature that will only be used by people who compile from source, and off they go. Whereas in other cases, I guess with OpenSSL, the kind of including things in releases makes that harder. It's just in the nature of the project. But hey, I walked into it with my eyes open, so it's my fault. And despite all of this, everything taking so long, it's nearly done, I hope. And I hope in the future not to be working on ECH so much. And I think that's my last slide. So if anybody has questions, I'll happily take them, or comments.
First, there's a typo. It's FAFO, not DEFO. So this is just plugging something. You mentioned rebasing is a terrible pain. And years ago, I had to do the same thing. And Victor here, he had a thing that would just slowly rebase, commit by commit until, to find the commit at which the conflicts arose.
Right.
And so we worked together because I was too slow. We made it bisect. So if you want that, I'll show you later. But it's in my gists in GitHub.
Okay.
And it will go through 2,000 commits easily. If there's like only 10 of those 2,000 that will actually cause conflicts, you only have to resolve conflicts 10 times.
Yeah, okay.
So it's very nice because it's the place where you needed to find the...
Yeah, I used to have that problem, but because we have this daily CI thing, we get a mail from, on the day it happens, when the issue arises. So it's actually that's not so much of an issue for us anymore.
And then one thing I should say, curl I know is a nightmare for DNS anything. I mean, you can't, if you set a timeout, it'll do alarm, and that's not thread safe, and all sorts of crazy things. So if you could make that better, that'd be great. There you go, more work for you.
Yes, thanks very much. Yeah.
Anybody else? All right.
The lights are strong.
Hey.
Hey. Okay, so I'm the maintainer of the DTLS branch, and I think a lot of what you're saying is some of the things I'm also. I don't like the word frustrated about, but I see that it takes a lot of time to get things through. But have you considered if some parts of your contribution could go into the code base because it's not really that tied to the ECH feature? Because I've been thinking about ways to kind of get all of these lines of code into the main code base.
Sure.
Gradually.
Not much, no. I mean, there have been a few small PRs that we kind of did that are outside of the ECH bit, but not so much, probably because the way I kind of wrote the ECH code was to try and add as little new code as possible. So the kind of if-def, OpenSSL, no ECH bits don't really do anything other than ECH. And so it's kind of, I don't know what the answer to this. It's just hard to see how do you kind of get a massive big change that's scattered all over the place, upstreamed in a, I don't know if there's an easy answer. So, I mean, if OpenSSL maintainers could clone themselves, that would probably help. But short of that, I'm not sure.
Anybody else?
Victor?
Sure. Is Shane still partnering with you, or is he helping you along now?
So this question was whether Shane was actively working. Not so much, no. He has kind of a little bit, but mostly he was extremely helpful with the HPKE stuff, but hasn't been actively working on it. I presume he's doing other things. So.
The reason I asked that is that there wasn't somebody else working on a branch like yours, perhaps a little smaller, where I was able to see it through. I had the cycles to work with the contributor. You can find somebody inside who's enthused about your project, who can collaborate all the way to see it through to the end. That can work well.
Thank you for volunteering, Victor.
I actually volunteered for you, and then I ran out of cycles.
Yeah.
Because I wanted to do this with you.
Yes. Yeah. I mean, if there's any OpenSSL maintainers out there who want to kind of work on this, I'd be delighted.
We had some.
Sorry.
There was one more question, and that will be it.
Yeah.
Yeah, I'm wondering, would it have made your life a lot easier if the TLS libraries had a way to do the DNS and you wouldn't have to do it in the various clients, like an API that allows you to say, connect to this machine and do all the DNS thing and figure out the ECH?
Well, Python kind of has that, right? So Python has a reasonable DNS library that has HTTPS or support. So that made integrating ECH into Python pretty straightforward. Should the OpenSSL library have something like that? I don't think so, because that's where you're going to get lots of failures. And probably applications need to deal with those kind of failures. And then also, even if you did that, then what are you going to do about DNS over HTTPS? And I don't think that would make life easier in general. But for applications, where they have already got good DNS client support, that makes life a hell of a lot easier. But it's not easy to do that. I think the curl example is a good one where they have, like, curl is a really good tool, but it's really hard for curl to do a great job in DNS because of all the ways it's used and all the weird DNS things that happen.